we'll see linear programming problems, LPP. In short, we write LPP, linear programming problems. We have discussed the graphical method of solution, so you know something about this issue. What we do, we have an objective function z. Generally, it is given as c1 x1 plus c2 x2 plus c3 x3 and so on. Can be written like this: ci xi, I equal to 1 to n. Okay, so this is our objective function. I'm just giving you a recap before entering the simplex method. This is our objective function. Okay, so this has to be maximized or minimized. This is the objective function, and we have certain constraints. For example, we have a1 x1 plus a2 x2 plus a3 x3 less than equal to, let's say, b1. Then next we have d1 x1 plus d2 x2 plus d3 x3 less than equal to b2. This type of constraints we have, these are called constraints. We can write them like this: aj xj less than equal to bj, where j is equal to 1 to n. Similarly, we have other constraints. So this is objective function, this is the constraint, or these are constraints. And one more thing is, these variables x1, x2 and so on, they are greater than 0. They are positive variables. This is a linear programming problem. Okay, so this is a recap. Now, if we have certain equations or inequalities and we get solutions for x1, x2 and so on, that is called solution. x1 equal to 2, x3 equal to 5, x4 equal to -1. So this set is called solution. Now, when we have a constraint that these are greater than equal to 0, then it is called feasible solution. Okay, and from these feasible solutions, when we are able to maximize or minimize the objective function, that is called the optimal solution. So these are the terms you should understand. Any type of solution is solution, but when they are positive, that is feasible solution. And from such a set of feasible solutions, when we are able to maximize or minimize the objective function, that is called optimal solution. Okay, now we'll learn a technique of transforming inequality into an equation. How? See, let's say our inequality is this: I equal to 1 to n less than bi. Okay, what we can do is we can add one variable. This means, let's simplify it: a1 x1 plus a2 x2 less than b1. Okay, less than equal to b1. This means if we add some, this is always less than this, or at the most it can be equal to this. So if certain variable is added to it, this can be an equation like this: a1 x1 plus a2 x2, and let's say we add s1 to it, then this inequality will become equal to b1. By whatever quantity this was less than b1, we have added to it. Clear? So less than equal to inequality can be transformed into an equation, that is equal to, by adding a variable which is called slack variable. Okay, so slack variable is a variable that can be added to the left hand side of less than equal to inequality, so that this side is now equal to this side. This is slack variable. And in case of an inequality which is greater than equal to, if this is like this, this means this is at the most it is equal to this, or it is always greater than this. Then if a variable is minus to this, this can become, let's say by s2 this is greater than this. So if we subtract s2 from this side, see, this is side, if we subtract s2, this greater than sign will go and this will become b1. At s2 equal to 0, this will be equal to b1. Otherwise, by whatever value this is greater than v1, we have subtracted it. So this type of variable is called surplus variable. Okay. So we can transform inequality into an equal to equation by, if it is less than equal to, we'll add slack variable. If it is greater than equal to, then we'll subtract the surplus variable. Okay. So now we'll consider two forms of linear programming problems. First is called canonical form. Canonical form of linear programming problem. Okay. And second is called standard form. Standard form of linear programming problem. So the first form, canonical form, its first characteristic is that the objective function is to be maximized. Okay, we maximize z. This is the first condition. Second is the constraints have less than equal to inequality only. We do not deal with greater than equal to in canonical form. Third is all these variables x1, x2, x3, these are greater than equal to 0. If these conditions are met, we say it is canonical form of LPP. Okay. Now, second form, standard form. In a standard form, again, we maximize z. This is not inequality, but it is equal to. Okay. Xi is always greater than 0. And there's one more condition, that bi equal to bi, the right hand side. This is always greater than equal to 0. This is always positive. Okay, then we say it is standard form of LPP. Clear? Canonical form and standard form. So this was second one. So we saw two things we can observe from these two forms, canonical and standard form. First is we are talking of maximizing only, maximizing z. And second is we are saying that xi should be non-negative. This is this. Now what if we have to minimize in place of maximizing? And what if one of the variables or more than one variable is negative? How to deal with that? See, maximizing z, what we'll do, if we have to minimize z, I should write it like this. If we have to minimize z means maximize z dash, where z dash is what? Minus z. Simple. So if we have to minimize z, we'll take minus z. We'll maximize minus z, that will be minimizing z. Okay. Secondly, if xi is, let's say xi is less than equal to 0, then what we do? We say xi is equal to xi dash minus xi double dash. It is less than equal to 0. We say it is this minus this, where xi dash is greater than 0 and xi double dash is greater than equal to 0. So now our condition is met, that the variables are, we only introduce a new variable, two new variables in place of one variable, where both are this thing. So this can be negative. We have dealt with this in this form. Okay. Let's consider this objective function z, 3x1 plus 4x2 plus 7x3. The inequalities are 6x1 minus 4x2 is less than or equal to 7, 2x1, 3x2, x3 greater than or equal to 10, and 2x1, 3x3 less than or equal to 3. We have x1 greater than or equal to 0, x2 greater than or equal to 0. We have to convert this into standard form. Standard form means we'll have to remove these inequalities by using surplus variables and slack variables. But one thing to note here is that x1 and x2 are greater than or equal to 0. Nothing is written about x3. So let's assume it is less than 0. So what we'll do, first of all, we'll say x3 is equal to x3 dash minus x3 double dash, where x3 and x3, these are greater than or equal to 0. Okay. Now we'll change the equations. See, 6x1 minus 4x2, we don't have x3 here, less than or equal to 7. So let's say we put a slack variable here, s1 equal to 7. So this is the first equation. Second is this one, 2x1 plus 3x2 plus x3. So in place of x3, we'll write x3 dash minus x3 double dash. This is greater than or equal to 10. So we'll put minus s2 equal to 10. This is surplus variable. Okay. And then third, we have this equation, 2x1. So 2x1 plus thrice x3 dash minus thrice x3 double dash, again less than, so plus s3 equal to 3. So now we have these constants where we have x1, x2, x3 dash, x3 double dash, s1, s2 and s3. These all are greater than equal to 0. And our objective function will be, see, I'm writing here only, our objective function will now become 7x3 dash minus 7x3 double dash. So this is the solution. We have transformed it to standard form of linear programming problem. We'll use it when we'll be solving linear programming problems by simplex method. We'll be using it. So you must understand this properly.